Now, let's continue to a one-dimensional traveling wave. Mathematically, we can use sinusoidal wave function as a standard graphical representation of a wave traveling on a string or any form of traveling wave. This is because sinusoidal curve can describe a smooth periodic oscillation of a continuous wave. As its name, sinusoidal wave implies a wave that look like a sine graph. The traveling wave equation can be written as y of xt is equal to a sine kx minus omega t plus phi. In this equation, y is the height of the wave at position x and time t. Position x is the distance along the string or the x-axis, and it is measured in meter. T is the time measured in second. A is the maximum amplitude of the oscillation, and it is measured in meter. K is the wave number, and it can tell us the wavelength of the wave by the equation k is equal to 2 pi over lambda. K is measured in radian per meter. Next is omega. Omega is the angular frequency of the oscillation, where this omega can tell us the frequency of the oscillation by the formula omega is equal to 2 pi f, where f is measured in inverse second or hertz, and omega is measured in unit radian per second. And last but not least is phi. Phi tells us the initial starting point of the wave itself. The wave equation above represents a wave traveling towards the positive x direction or to the right, and if we want to change direction so that it will travel towards the negative x direction or to the left, we can write it as y of xt is equal to a sine kx plus omega t plus phi, where kx and omega t has the same sign. If they have the opposite sign, they are traveling towards the positive x direction. Another information that we can get from the traveling wave equation is the velocity of the wave. We know that velocity v is equal to frequency times the wavelength. By relating the relationship between the k and omega, we can see that 2 pi over k times with omega over 2 pi will give us omega over k. Therefore, we can say that v velocity is equal to omega over k.